back to the series on exponents, and today we're going to be going over the second episode, which is an overview on more complicated operations with exponents, as well as the order of operations with exponents, and we're finally going to get into the special cases, which are a little more advanced, the negative exponents and the fraction exponents. Alright, let's get started. So, we can start off with the basics. So just to review, we're going to go over addition, so we have 2 to the power of 2 plus 3 to the power of 4, for example. Here we're using addition as the operation between two exponents. Now regardless of whether they are the same base or not, since it's an addition, we just treat them separately, then evaluate. So in this case it's 2 times 2 plus 3 times 3 times 3 times 3. That leaves us with 4 plus 9 times 9, which is 81. Final answer, 85. What if we had a subtraction? What if we had 4 to the power of 3 minus 2 to the power of 1? 4 to the power of 3 is 4 times 4 times 4 minus 2, since 2 to the power of 1 is just 2. Here we have 4 times 4, which is 16. And then we're going to multiply 16 times 4, and that leaves us with 64. So it's going to be 64 minus 2. Final answer, 62. As you can see here, we did the same process as the addition. We just treat them separately, then deal with the operation. Now, the separate cases, which have different rules, are the multiplication. So I'm going to do two examples. One multiplication operation where the bases are the same, and another one where they're not the same. Alright, so for the first one, I'll go with 3 to the power of 3 times 3 to the power of 2. Now, as the rule, if you remember from last episode, when we're multiplying two exponents and we have the same base here, 3 and 3, we simply add the exponents. Meaning, I just rewrite the 3, and what's 3 plus 2? We're left with 5. Now, if I want to evaluate it, I simply treat it like any other exponent. 3 times 3 times 3 times 3 times 3. Okay, this gives me 9, this gives me 9, this gives me 27. Then I multiply 27 times 9, and that gives me 243. Cool. Now what if we had an example where the bases are not the same? What if we had, switch up the color here, what if we had 3 to the power of 3 times 4 to the power of 2? Since they're different bases, I can't simply add the exponents. I'll have to treat them separately just like I did for the first two cases. So, 3 to the power of 3 is 3 times 3 times 3 plus, since we're multiplying, we're going to keep it as multiplication between them, 4 times 4. So now I've written this one out, and I know that between them is the operation of multiplication. So, 3 times 3 is 9, times 3 is 27, 4 times 4 is 16. So, what happens when you multiply 27 times 16? You get a pretty large number, you get 432. Alright, now to re-elaborate the similar base rule, what if we're dividing? Does the rule change in terms of common bases? It doesn't. There's just a different operation for the exponents. So if I have 3 to the power of 3 divided by 3 to the power of 2, since it's division and the bases are the same, all I have to do is subtract. This time we're subtracting the exponents. So I simply rewrite the base, which is 3. 3 minus 2 is 1. And what's 3 to the power of 1? It's simply 3. Now, if we don't have a common base, if we have 3 to the power of 3 divided by 2 to the power of 2, different base, I can't do the subtraction thing. The subtraction rule with the exponents. 3 to the power of 3 is 27, as we've discussed earlier, divided by 2 to the power of 2, which is 4. Here it'll give me a decimal, so I'll just leave it in a fraction form. Alright, that's it for our simple review. And I'll get started into the mixing and mashing of the operations altogether so that we can begin doing the more complicated ones. So, first things first, I'll put one equation which has many different pieces to it, many different forms of these operations which we just worked on, and we'll see how we fare with it. So, first one, what if we had 3 squared minus 2 to the power 4 times 6 to the 6 times, or 6 to the power 1 times 6 to the power 4. And it's all divided by 17 squared. Okay, so we've got some subtraction, we've got some multiplication, we have the parentheses multiplication here, and we have our denominator, meaning we're dividing. So, what's our first step? Our first step is to elaborate what's inside the parentheses. And just to recap for those of you who don't remember, P is what we start with, the parentheses, then we go for the exponents, ped, mas, D is division, M is multiplication, A is addition, and S for subtraction. So keep this in mind, pedmas, 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 something that we should remember because it shows us the order of operations for any equation, but it will definitely come in use for this one. So if we have 3 squared, that'll give us 9, so I'll just write a little 9 above it. 2 to the power of 4, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we're left with 16 here. 6 to the power of 1 is 6. 6 to the power of 4, using my trusty calculator here. 2, 3, 4. Well, that is a very big number. 6 times 6 is 36, times 6 is 216, times 6 is 1,296. And on the bottom, we have 17 times 17, which is 289. So let's rewrite this here so that we see exactly what we're working with. We have 3 squared, which is 9, minus 16, which was 2 to the power of 4. Then we have 6 times 1,296, or, since we recognize that both of the bases here are the same, we can just write it as 6 to the power of 5, because we simply add the exponents. Then we put it over 289. Now, let's simplify a little further. Inside of here, we're going to do 9 minus 16, and that gives us minus 7. And then for the 6 to the power of 5, we do 1,296 times 6, a very large number, 7,776 over 289. And then we multiply the top, because we have to get rid of the parentheses here. We multiply 7,776 times minus 7. 7,776, very large number, times negative 7. And that leaves us with a very large number on the top, negative 54,432, all over 289, divided by 289. That leaves us with a negative 188.35 if we round to the second decimal. So, we see here how we can apply the different rules whilst keeping in mind the order of operations. Let's do another example, just so that we're sure that we understand it. So this is going to be our second example. This second example, I want to focus on the rules with similar bases. So when we have similar bases, just a reminder, when we're multiplying two exponents with a similar base, we add the exponents. When we're dividing them, then we are subtracting the exponents. So if I have 2 to the power of 4 times 2 to the power of 5 times 6 to the power of 2 times 6 to the power of 2 divided by, let's see here, 6 to the power of 3, multiplied here, the dot means multiplication, by 6 to the power of 2 over 3 to the power of 4. Okay, so as we all know, when we have fractions multiplied by a fraction, we simply multiply the top and we multiply the bottom. So what we're left with here is 6 squared times 2 to the power of 4 times 2 to the power of 5 times 6 squared times 6 squared, it's not very clear, times 6 squared over 6 cubed times 3 to the power of 4. Now, to apply PEDMAS, First, we can look at what we can eliminate, since we have a denominator and a numerator, which have similar bases here. We have 6 to the power of 2, and we have 6 to the power of 3 on the denominator. And as we looked at in the previous rule that we discussed, similar base, right? 6 and 6, meaning we can take 2 minus 3, and that leaves us with 6 to the negative 1. So here we're left with 6 to the negative 1. Here we've introduced negative exponents. And I'll get into what that means exactly, but then we can dive a little deeper so that we get a full understanding of it. Okay, then for this multiplication, we have the exact same base, so we add the exponents. We get 2 to the power of 9, very large number. Then we open up the other parentheses, 6 to the power of 2 times 6 to the power of 2. We add the 2's, we get 6 to the power of 4 over 3 to the power of 4. Okay, now before we expand everything, which is going to be a very long process, I would rather see what I can do with this negative exponent. When we're dealing with negative exponents in any order of operations, it's best to turn them into positive exponents because they're easier to work with that way. So here, if I were to turn it into a positive exponent, 6 to the negative 1 is equal to 1 over 6 to the power of 1, meaning that I was able to get rid of the negative sign by putting it in the denominator, yet maintaining the coefficient of the exponent. So if, for example, it was 6 to the negative 2, it would be 1 over 6 to the 2. 6 squared. Or if it was 6 to the power of negative 4, that would be equal to 1 over 6 to the power of 4. Easy enough. So here, when I have 6 to the negative 1, and I want to get rid of the negative sign, it simply moves to the denominator. So here I'm left with 2 to the power of 9 times 6 to the power of 4. And in the denominator, we have 6 to the power of 1, which is simply 6, times 3 to the power of 4. Now I think we understand it so far. If we have a multiplication of different bases, we simply expand each one, and then we solve for the final answer. So, without spending more time on the operations, I want to go over the negative exponents. So just as a quick recap, if we have any base, b for base, with a negative exponent, n as in any number, but it's negative, it'll be equal to 1 over the base to the power of the n value, not negative n, gets rid of the negative by putting it in the denominator, yet maintains the coefficient. So if I were to show you a quick example of what that looks like, if I have 2 to the power of negative 4, it'll be equal to 1 over 2 to the power of 4. If it was 2 to the power of negative 2, it would be 1 over 2 squared. And it doesn't have to be 2, it could be 3 to the power of negative 5, it'll be 1 over 3 to the power of 5. Now, since it's a negative exponent and we're putting it in the denominator, it works opposite in terms of the growth of the number. So, what I mean by this is that when we have, for example, any base, and the n is very large, let's say we have 2 to the power of 2 versus 2 to the power of 4. Since the number up here in the exponent is larger, we know that this one right here, the 2 to the power of 4, is going to be much larger than 2 to the power of 2. Exponentially larger. That's where that word comes from. Exponentially comes from the word exponent. So here we have 2 to the power of 4, meaning that we're multiplying the result of 2 to the power of 2 by itself twice after the final result. Much larger. The opposite happens when we're dealing with negative exponents. That's not very clear. And so here if we have 2 to the power of negative 2 versus 2 to the power of negative 4, this number is bigger. Because the larger the negative number, meaning, or should I say the lower the number is, if it's negative 10, for example, it'll keep getting lower and lower and lower and lower. So, and the reason why, if we explain it in another term, if we have b to the power of negative 10, for example, that'll be equal to 1 over b to the power of 10. The larger the denominator, the smaller the overall number is. If we compared this to a pi, so let's say I had a little pi here. Let me fill it in. And I asked you, how much of this pie would you like to take? You get to take as much as you want. Let's say you're hungry that day and you want to take half. The number in the denominator is only 2, a very small number. And you're getting a pretty big piece of the pie. All of this would be yours. But if you're getting, instead of half, an extremely small number, you're just getting a tiny piece of the pie. 1/2, we divided it into 2. Here, let's say this is a 1/36th of the pi. You're getting a tiny, tiny chunk of it. Same thing applies here. When it's exponentially large in the denominator, the overall number will be very small, especially if the numerator is only 1. Okay, enough about negative exponents. In the next episode, I'll be going over fractional exponents. Unfortunately, we don't have enough time for today, but stay tuned, and I'll hope to see you in the next episode.